Good evening, everyone from Hong Kong, Sydney, and good morning to the one who joined us in London. Welcome you all to the webinar Teleco Talk, Science and Technology of Battery Fire Safety by Hong Kong IE Fire Division with speaker from Imperial College. For this webinar, we had over 610 enrollments, including engineers from Hong Kong, Sydney, and London. And currently, we have over 270 joined the event already. Please bear with me for a couple of minutes as I would like to share with you all on how we make this event happen and would like to thank you several parties. Each year, the Fire Division will hold annual overseas Teleco visits to exchange fire engineering knowledge with overseas experts. For the 2020, we planned it to Sydney, Australia in Q1. Throughout the preparation, we were connected with the Hong Kong IE Australian chapter. With help from engineer Mei Yang, we were introduced to the Society of Fire Safety New South Wales and successfully organized the event and planned to visit the New South Wales University, the Fire and Rescue New South Wales. They are the FSD in Sydney. Several local engineering consultants to visit the Sydney Metro, Sydney Opera House, the ICC, etc., and attending a CPD organized by the Society of Fire Safety. However, due to the outbreak of the COVID-19, the trip is put on hold, but we will have it back again. Although the trip didn't go ahead, but it doesn't stop us in having sharing with overseas experts. With assistance from the Society of Fire and Safety Chapter Chair, Engineering Edwin Ong, we were introduced to Professor Rain from Imperial College in having this delightful sharing with us. I would like to take this opportunity to thank you, Ms. Mei Yang from the Hong Kong IE Australian Chapter, Engineer Edward Ng from the Society of Fire Safety New South Wales, and other professionals from Sydney and London in helping us in make this event happen. The last but not the least, I would like to thank you, Professor Ring, in accepting our invitation, and it is our pleasure having Professor Ring from Imperial College to share with us. Professor Ring is from Fire Science at the Department of Mechanical Engineering, Imperial College, and he is also the Editor-in-Chief of the Journal of Fire Technology. His research is centered on heat transfer, combustion, and fire. The purpose of his work is to reduce the worldwide burden of accidental fire and protect people, their property, and their environment. His research profile is ample, but over the last 15 years, he is best known in 3 areas: how polymer and works ignite so we can avoid fire from starting, how engineers can design better structure that resist fire, and how wind fire spread and how to fight them. He leads the research group Imperial Hazard Lab with current counts with 3 postdocs and 12 PhD students. Due to the COVID situation in UK, Professor Ring has pre-recorded the sharing for us, and he will join us in Q&A section live. If you have any question, please post it to the Q&A boxes during the presentation or at the end of the presentation. To help us answer as many questions as possible, so please ask 1 question per post. If you have more than 1 question, put them into separate posts. If your question has already been asked by someone else, please use the like features instead of the posting. We will try to prioritize the most popular question first. So let's have the sharing from Professor Rain.
Hello, welcome to my lecture. I am going to be talking about battery fire safety and the science and technology that we know about it. This presentation is an overview, mostly based on the research that my group at Imperial College London and collaborators have conducted over the last few years. My name is Guillermo Rey, and I am Professor of Fire Science at Imperial College in London. The talk will have four parts. I will have an introduction on the importance of battery fires and its significance, a little bit about the ignition mechanisms that are known in the literature and the ones that we have contributed to from my group, about fire protection, very important in an audience of engineers, is to know how we can actually avoid these fires from happening and how can we protect ourselves, our property and the environment from these fires, and the challenges that are being faced by industry. As context, I want to show you this plot of the number of fire deaths per 100,000 inhabitants over the last 100 years in the United States. The number of fire deaths in this plot are obviously of all causes known to humanity. These are fires that happen in living rooms, in kitchens, in the exterior of the building. It shows a very successful story where over the last 100 years, engineers have protected citizens to reduce the number of fire deaths by 90%. It is a very impressive success story. This is not only in the United States as shown in the data, but it's in every single Western country where the data has been investigated, and many developing countries. The only thing is that the United States and the UK are the only countries with a long-standing, long-term, good quality data set of fire death quality. That's what I use in America. However, when we look into what is happening around the world, not just Western countries, what we see is that the problem with fire deaths is very large. Fire accounts for 5% of the injury-related deaths worldwide. Injury-related means that we have to discount natural causes or sickness, this injury-related. Compare that 5% of fire with 2% that is caused by war. And you realize the big problem that we have with fire in the planet. Even in good cases like the United States, the UK, and many Western countries, where we have a successful story of protecting against fire, we still have the issue that it comes with a tremendous cost. We're talking about billions per year in every one of these countries, and this money could be used for other things. If protection were to arrive with a lower cost, we could use this money for education, for development, for infrastructure, for neighborhoods. And this comes on top of a demand from citizens that we should protect more and better. In this context, and with already a busy agenda for fire protection engineers, we have new arrivals of threats. Lithium-ion batteries. Lithium-ion batteries are very important technology presently and in the future, an even more important one, and is being used for energy storage of all types of sizes for transport, especially vehicles, for example. There is also aiding aviation and navy and consumer electronics, and it has led to an absolute revolution of electronics and power and mobility and sustainability and renewable energies. And as engineers, we love this. We absolutely love to see society doing things that could not be done and problems being solved that could not be solved before. However, in the case of lithium-ion batteries, these very high energy devices, some of them, many of them, have a tendency to ignite, burn, and release gases. This is a very well documented tendency, which is not fully understood, which means that industry cannot fully avoid it yet. They are in the process of fully learning what is happening, why it's happening, so it can actually be stopped. Although fires or incidents, or ignition incidents with lithium-ion batteries are rare, statistically, we see a lot of fires, but that's because there are a lot of batteries. No matter that it's rare, lithium-ion batteries pose a fire hazard. This is a fact, which is actually very different to other fire hazards known to engineers, and this is something that is very concerning, because the ignition route is different from a lithium battery than from a sofa being ignited because of a cigarette nearby. The rate of spread is much faster than the typical rate of spread of a fire. The battery has a very violent process of ignition, not a slow process of ignition. The duration of a battery, of a big battery fire, is very long. We're talking about hours and days, much longer than other fires that we are used to protect ourselves. The gases that are released when ignited, and even more when they're not ignited, are very toxic. It's a type of chemistry that is not a hydrocarbon chemistry of plastics and natural materials. And suppression. We still don't know how to suppress these fires, in particular the very large ones. For example, electric vehicles. It is a serious concern how to suppress these fires. In this context of success technology, future growth of this technology, but new questions, we are faced with all the situations where we had fires. We are seeing that as the energy density of these devices grows, the reactivity of the device grows, and the failure potential and the consequences of the failure grow. Question that we have, is this the next big issue of energy innovation? Because what we are seeing right now is that industry and authorities are not putting enough attention to the problem of lithium-ion battery fires. They're putting some attention. In fact, actually, they're putting attention after fires happen. So they're having a reactive mode, slow reactive mode, whereas we think that they might need a fast preventive or ahead of the game mode. Remember the Dreamliner when it was inaugurated in 2013? What happened to the battery fires that actually over the week of the first flights of the fire? It almost derailed a new aircraft type, the Dreamliner. Or what is happening with electric vehicles. These are some cases that have been documented in a recent literature review from actually researchers here in Hong Kong on the presence of fires in electric vehicles. Many of these fires are caused because there is an accident, there is a failure, there is a problem, and then the battery ignites. Ignites in a way that if it were not, that it would not have ignited, and it would not have burned this way if it to be a conventional fuel vehicle. Also, and this is more concerning, we see cases where it is not because of an accident or an intervention or a failure, it actually is a spontaneous ignition. The car was parked in the garage and the electric vehicle suddenly burst into flames. Why is that happening? There was no clear accident abuse beforehand. Another case that is very concerning, precisely because of the monetary value that is involved, is when battery fires happen in warehouses, in these big warehouses where hundreds, millions of battery cells are stored. Very well documented. Some of these cases, we don't even understand why they happen. The hinting to that there are mechanisms where we put so many batteries together and we cannot still explain, and the authorities and the standards and the industry cannot still explain what they have happened. Or a new fire hazard when lithium-ion batteries are discharged and sent into the rubbish. They are sent to waste. There is this big movement. I just took the slide that is used for it. In the UK, has started. It's called Take Charge. And they name battery fires as zombie fires because you think that the battery is dead, it's not doing anything, but actually it suddenly catches fire and produces a massive fire in a recycling plant or in a waste facility. These fires are becoming a serious issue. Discharged unwanted batteries that have reached their end of useful life, thrown into the garbage and causing serious fires later on in the recycling facilities. So this is just an example of a UK movement, Take Charge, but I'm sure it's happening in many other places. In this table over here, I on purpose am covering the content of the table. I don't want you to start reading it just yet. It's a table that summarizes the most the most important fire issues that have happened in the last 20 years, and this was done up to 2019. Now in 2021, we actually would need to update the table because in the last 2 years, there have been a significant number of recalls and accidents. What I want to call your attention when I show you this table is that every single sector of industry where lithium-ion batteries are used has been affected by big fire problems. And two, that if you sum up the cost that these fires and the recalls of products that have led after the fire, if you sum up the cost that it has made, you see really large costs, losses. Some of them have actually shaken the companies or the products that they were launching when the fire happened. You can see the sector of cell phones or laptops, electric vehicles, aerospace, hoverboards like toys, marine shipping, and any storage systems in our houses for electric circuits. These are different companies. These are the years that had happened, and these are a little bit of comments of what happened to it. Some of them, many of them, led to big recalls, and some of them are very prestigious systems, engineering systems. Some of them you would be surprised that engineers were not able to stop it. For example, Model S of Tesla, Samsung Electronics, Nokia Electronics, Boeing, Jaguar. These are not cheap systems that were done in a hurry and had an effect that they discovered later on. These are high-end engineering products that still are facing big failures of battery fires. This is also a problem for fire engineers. It's not just a problem for the industry and authorities. And I know this quite well. I'm from early on. In 2016, I was conducted a survey to fire engineers worldwide, 100 fire engineers worldwide, all of them quite famous. And I wanted to know I surveyed that because I wanted to know the trends. Where is the field of fire protection engineering going? So I had a conversation with them about what is changing in fire protection engineering and what are the causes and the systems. And there was a specific question when I highlighted 16 fire protection engineering systems. And I asked them to order them in terms of which one is most affected by change, which one is actually changing and making fire engineers have to look into new things. And these were the top of them. These were the top 6. At the top was new buildings, followed by timber buildings, followed by building facades. This was before Grenfell Tower happened. Number 3, building facades before Grenfell happened. If I were to run this survey now, this would be at the top. Number 1, building facades. Number 4, battery storage. So out of 16 important fire protection systems that were changing, already battery fires in 2016 were considered to be the top 4. I think that if I were to be running this survey, I will be getting facade fires at the top, followed by battery fires. Just to give you an idea of how important it is for a fire engineer, the fact that these systems are arriving, they are already here, and we don't fully understand the ignition, the flammability, and the fire behavior. Why would batteries catch fire? There are several reasons. The science has settled to 5 reasons why a battery catches fire. They're typically called abuse, because by abuse conditions, what they want to highlight is that it's a failure. It's not meant to happen. It's not part of the design process. It's accidental. And they highlight this as an abuse. So it could be that the battery has been abused electrically, in the sense that the charge or the discharge is too fast or beyond a limit, and that can cause an ignition. Or it could be mechanical abuse. For example, there have been a nail going through the system, or there have been shock, there has been heat, there has been a dent into it, there has been mechanical damage done to the battery that can actually produce a response of the battery as an ignition. It could be thermal abuse. This could be thermal abuse in the sense that the battery is at high temperature because it has been brought to a high temperature very quickly, for example, through a nearby fire, or it has been brought to a high temperature very slowly, being in a hot environment. Any type of thermal abuse can actually lead to a fire. It could be that the battery has defects that have not been controlled on time, and these defects later on appear as a spontaneous ignition. What would be the cause of those defects? And the latest one that actually another group at Imperial College we are leading is self-heating ignition, in the sense that reactions that are internal to the process that are not really due to an abuse, they actually are part of the life cycle of the battery, can actually lead to heat inside the system. And if this heat is not evacuated fast enough because there is not enough cooling, it can lead to a fire. So fire in all situations is because there is a heat source within the battery because of electrical, mechanical, thermal, a defect, or self-heating reasons. That could have a wide range of chemical paths, but all of them arrive to heat, and then this heat in an unsafe manner cannot be balanced by cooling. In a safe manner, the heat that is being generated by all these abuses, if there is cooling, there is heat dissipation, that balance it, then actually these abuses or these conditions will not lead to a fire. But if the heat that is being generated by these reactions cannot be balanced by heat dissipation or cooling, then the temperature will continue growing and it will lead to an actual fire. These are the 5 mechanisms known in the state of the art as what can lead to a lithium-ion battery fire. I want to tell you a little bit more about the last one, the self-heating one. Self-heating ignition is one that we have studied in my group at Hazla and Imperial College, and I want to tell you about it. First is that self-heating ignition is referring to a spontaneous behaviors. It doesn't require external event. It doesn't require an accident from the outside or a person or an event from outside. It's endogenous. It's part of the system. It's a spontaneous external reactions. Many of them are possible within the complexity of electrochemistry, complexity of a battery, that can be started at low ambient temperatures. There is no requirement for the battery to be a very high temperature inside a fire already to develop these reactions. These reactions can start at low temperature and ambient temperature. And if there is insufficient cooling, it can lead to what is called thermal runaway, which is a quick and unbounded growth of the temperature, well beyond what is happening in the environment. I explained this to you. These are laboratory measurements of a lithium-ion battery, commercially available, at different stages of the self-heating process. In black is the temperature of the environment. In this particular case, the battery was actually inserted into a chamber that was heated at a high temperature, about of 100. The temperature was about 170. The temperature of the oven. So you would say that's a temperature, that's a high temperature for a chamber, and that is true. I'll explain to you the meaning of that. And this is in red is the temperature of the battery. And you can see that upon the battery entering the chamber, it starts to increase its temperature, or rightly so, it's being heated up by the chamber's temperature, and it reaches what is called the crossover point, and it has ended the first stage. The first stage is the battery heats up to the temperature of the environment. But then look what happens. The battery is able to cross over the temperature of the environment. Why would the battery be able to go above the temperature of the environment? What is causing its temperature increase above what initially was actually providing the heat? That's the second stage, where actually self-heating starts to happen. And the temperature starts to have, and the battery starts to have, it starts to change its appearance in color, and we can start to see degradation. And then there is a point where thermal runaway happens, this over here, very quickly, within seconds. The temperature of the battery goes well beyond 200, 300, 400, and ends up being in a fire. You can see that in the third stage, the proper thermal runaway, the battery has changed its physiognomy completely. It has been degraded, it has swelled, it has lost some of its coating, the internal structure has been altered, the anode, the electrolyte, the cathode, the separator, they have actually been modified by the thermal process. The chemistry obviously have been modified, and maybe actually even the vent that some lithium-ion batteries have over here has opened. This is the indicative of a big failure. Stage 3 is a big failure. Stage 2 is the tail that the failure is going to happen, and stage 1 is it is ongoing to its failure. Now, someone might say that is very interesting mechanism that is endogenous to the battery, is spontaneous and internal, it's not external, but it's because the battery was set at a very high temperature, and that is true. However, we see a very clear trend that by stacking batteries together, the critical temperature of the environment that actually makes the battery thermal runaway drops. So this is the critical temperature of the environment, and as you put more batteries together, this is 1, this is 4, the temperature goes down. Why would the temperature go down, the critical temperature of self-heating ignition go down with the number of batteries? Because there is an inability to dissipate the heat, to cool down the heat that is being generated by these reactions. And that is the process of self-heating ignition. Just to note that these batteries were not connected. These batteries were what is called open circuit, or in conditions very typical, like in a storage. These were not batteries that were charging or discharging or being used electrochemically speaking. They were just open circuit, standing there, and the reactions that cause the self-ignition are reactions that are internal to the electrochemistry of the process. We have done experiments up to 4 cells, and we would love to do experiments at even more cells, but unfortunately we don't have the ability, the funding, we haven't found a partner yet to do these experiments, but they will happen at some point. In the meantime, what we can do is we can use theory and well-known theory of self-heating ignition that has been involved in Nobel Prizes to estimate, to calculate ahead of time what is the temperature, the critical temperature, as we increase the volume to area ratio, which is the same as increasing the volume of a stack of batteries. And what we say is that these are our experiments over here with just 4 batteries, but when we go and we put many of them together like in a box, and then we put all these boxes into shelves, and then we put these shelves in racks, and we put these racks into a warehouse. When we have very large storage sizes of batteries, we could be starting to see self-ignition at temperatures that are drastically lower than the ones that we saw in our experiments, much lower. And this 40 Celsius for a very large storage capability is for a very specific type of batteries that we got commercially, for which actually we are not even concerned about their reactivity. The batteries that we use in these experiments are not particularly reactive batteries, are actually quite rather safe batteries. Imagine if we were to do these experiments with batteries that are unsafe, that are not well designed, or that they have internal defects, or that actually had been used and they were thrown to waste. This plot over here will show that the capability of the batteries to self-ignite without an external event would be quite strong. One question that we ask ourselves is, but what can we do to avoid this mechanism of self-ignition while the batteries are being stored? And that's a very good question. We could do the experiments, hundreds of experiments, to look into the alternative ways of, for example, arranging the batteries inside the storage boxes, or we could use computer models. So the first thing is we develop a computer model of heat transfer and chemistry. We compare the model to predictions. So we compare the model to experiments that have done in the literature. This is the temperature of the battery. This is time. And in dots, we have experiments at different temperatures of the chamber. And in continuous line, we have the model in predictions. We can see that the model of heat transfer and chemistry is able to predict previous experiments. So then we launched the model to look into details that were not captured in the experiment. For example, inside the battery, inside the box, this is the box. It's a box of batteries, like the one that we see over here. This is that the batteries have been stored, cylindrical batteries, and this is the temperature. And what we see is that upon the box being inserted into the hot environment, which is about 130 Celsius, you can see that the center is cold and the edges are hot. That's because the heat is coming from the outside of the box. But then the box starts to heat up. And there is a point where the whole of the box is at the same temperature as the environment. It has reached equilibrium, and that's very nice. But if the temperature of the storage is above the critical, then what happens is that the battery doesn't stop there. It continues generating heat by spontaneous reactions, and the dissipation is not enough to remove the heat, and then the battery starts to increase, the box and the batteries inside the box start to increase its temperature, and it starts to march towards the stage 3 self-heating ignition thermal runaway. Things that we could do, which is turn over here, we could store the batteries with a different spacing. Creating space between them gives actually different ability to dissipate the heat. Or we could use different materials between the cells. We could put different polymers, different foams, different wrapping materials, which mostly are there to separate them electrically and mechanically, so they actually don't hit each other. But if we put them too close together, then they cannot dissipate heat, and actually the box then it becomes more prone. This box over here, where they're packed together, is more prone to self-ignition than this box over here. There is more space. We can see this in this prediction. This is the critical temperature of the environment that we are seeing for a box. We are predicting for a box. And this is the number of cells inside that box. You can see that as we increase the packing ratio, we can put more batteries. But as we put more batteries, we are reducing the critical temperature for ignition. This box over here has more batteries. That's very nice. But the inability to dissipate heat of this box makes its critical temperature to be even lower than the one where we had less batteries. So we can put them back together, but then we might be having more fires, which will lead to eventually the big loss of millions of cells in one single fire event. What can we do as engineers to avoid this? There is plenty of things that we can do. Fire engineers have developed the concept of layers of protection. This is developed to make the world safer, to protect people, their property and the environment. And we can borrow this concept, for example, to think of 4 layers of protection that can be used in a battery fire. For example, we could prevent the ignition, the self-heating, the abuse, or the thermal runaway by altering the chemistry of the cathode and the anode, the electrolyte, the separation. We can do many things, and we're going to see a few of them. Or we could, or no. And if prevention fails, if this layer is breached, then the next layer is there to protect us as well, which is detection. If there is a fire, we need to detect the fire as soon as possible. This is not just a smoke alarm or a visual detection of a flame or a hotspot. These could be devices that are inside the battery, like the battery management system, for example, that is able to detect anomalies in the voltage, or anomalies in the temperature, or anomalies in the deformation and the swelling, for example, or overpressure. Once the detection has come into action and hopefully has not been breached, we also have the compartmentation layer, which means that if there is a fire in one cell, make sure that it doesn't propagate to other cells. If a fire is propagating from one cell to another, make sure that it doesn't propagate to a different module. And if a fire is propagating in a different module, make sure that it doesn't propagate to a different system. So there are layers of compartmentation to make sure that the fire remains in the original compartment or the original sub-part of the system. And another important layer is suppression. The fire has happened, has been detected, maybe compartmentation is working or not, but you could actually suppress with a gas, with a liquid, with alternative ways that we're going to discuss now. So many things can be done to protect from battery side. This is a literature review that we did very quickly of different key technologies that exist in prevention. For example, I will highlight that the use of different electrolytes and additives to electrolytes can actually dampen the reactivity of the system and the flammability of the system. It's important, for example, if there is an ignition event, that the electrolyte or the plastic casing, for example, doesn't become a fuel that leads to a fire. Compartmentation, there has been development on containers, sealed containers, to make sure that if there is a fire inside the container, the outside of the container doesn't get affected by the toxic gases, by the heat, or by the fire itself. Detection, there is ongoing work to use anomalies in voltage and temperature deformation, not only to detect the fire, but to detect that the battery is in a stage that is going to lead it to a fire, or typical presence detection of heat and smoke of all the gases, which is typically done in fire safety engineering. And suppression, which could be by removing oxygen or providing tons of cooling, chemically speaking as well, or isolating the system, or something that is actually being done as well with electric vehicles is flooding, which is completely immersing the battery or the module or the package or the car in a container of water. Make sure that actually it provides plenty of cooling, and it also discharges the battery by, for example, adding salt to the water. In this literature review that I was hinting to, we have also seen the importance of size. These are the size that are involved in lithium-ion batteries. We have the size of the arrangement, the molecular arrangement of the materials that are being used, or the microstructure of the elements that are being used, or the components that actually make the battery, like the anode, the cathode, the separator, and the electrolyte, or the cell. The cell is, from the point of view as an engineering, the first component that actually makes sense, that itself provides a unit of use, the cell. But the cell is very small. We're talking about fractions of a meter. Then many cells put together, maybe hundreds of them, create a module. A module is definitely very useful. We're talking now in the order of meters now. And then many modules put together create a pack. A pack can be in the order of several meters. And across all these, we have different sizes. Not only different sizes, but what we see is that, for example, there are different interests for research. Most research, and we did a meta review of this, most research has been conducted at the cell level, sometimes by altering the components or the microstructure. Okay? But most of the research, much of the understanding, most of the knowledge on battery fires are at the cell level. However, the true worry of industry, citizens, and authorities and engineers is at the pack and module level, because these are the fires that really matter in terms of safety, hazards, and losses to life or economic losses. And there is a mismatch already that we identify in the literature between where solutions and knowledge is needed and where actual solutions and knowledge is existing today. Little by little, as we move forward, communicating industry and research, we would like to see more research in the module and the pack, such that more solutions can be developed where actually industry needs them. These are the results that we saw of our meta review of the research on lithium-ion battery fires. It's a heavy and complex table. I understand this. We can look into the top. I'll explain to you what it is. We have a set of categories. We look into the literature, and we look into what was the cause of the fire according to those papers, the scale of interest, and the protection layer. And the three of them are repeated here. And then we look into not every single paper in the literature directly, but we look into the reviews of lithium-ion battery papers, fires in the literature. So this is one 2017, this is Mauer 84. Sorry, that's not the year. That's the number of papers. So Wang et al. Had 217 papers. Mauer et al. Had 84 papers. Wang et al. Has 373 papers. You can see already some of the big ones. This one will be one of the small ones long, and this one over here will be one of the big ones, with 337 papers. But you can see when it goes inside, what is this? For example, cause of the fire, and mechanical abuse, electrical abuse, thermal abuse, also an internal circuit. But you can see some of them are not even mentioned. Some the literature review, some of them are not interested in the cause. The ones that do, they cover quite well the wide range of causes right? This one, for example, has more about mechanical and very little about intense or liquids, but you can see that it's good. The literature is looking into all these four causes. It's not looking into self-heating, which is the fifth one, but that's something that, as I showed you before, is more recent. My group is leading this research in the last few months, few years. When we look into the scale, what we see is the component scale, cell, module, and pack. You can see most of the research is in the component, followed by the cell, very little in the module, very little in the pack. And this happens pretty much in every single paper in the literature, with maybe the exception of Long et al., which has a significant amount of the pack, or Sun et al., that has a significant amount in the pack. Those are exceptions. Most other ones are saying most of the research is at the component and cell, the small scales, and very little on the large scale. And then when we look into the protection layer that is being reviewed in these papers, P stands for prevention, D for detection, S for suppression, C for compartmentation. We can see most papers are doing prevention, 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 prevention. Very little on detection, sometimes nothing on suppression, nothing on compartmentation. This will be a little bit touched upon. Okay, this one very little in detection, very little in compartmentation. So what you see is that there is a lot of knowledge at the small scale. There is a lot of emphasis in the prevention. We need more at the large scale. We need more at the suppression, compartmentation, and detection layers of protection. We also did in this review, we reached out to industry and we asked them, what are the challenges that you're facing? What are the worries that you're having right now? And the worries of industry are the circles. Industry, so they do have concerns about regulations and standards. They want them to be more realistic. They want standards to be more realistic and to be more clearly defined and to be harmonized. And they don't see that happening yet. They want more about detection and early warnings. They want more guidance about what is going to be the emergency response and how do we learn from the other industries that are dealing with this, and is it possible to have databases of knowledge on transport and in life? What do they do when they're transporting and storing the batteries? What do they do when the batteries are discharged and put to waste or recycled? What do they do about avoiding ignition and propagation? What do they do about the types of abuse that are known and the types of abuse that are being learned as we speak? And then in the squares is what we see that research is doing on needing. For example, research is saying that they need multi-scale approaches, not just one single scale. That there is a need for better detection, that there is a need for better suppression, and there is a need for thermal barriers for compartmentation. So this all together is showing the industry and the research put together what they need now and what would happen in the next few years. So with this I'm finishing. Just to conclude that although it's statistically rare because of the very high presence of batteries all around of all sizes in our lives, lithium-ion batteries pose a serious fire hazard. Even it is possible that a spontaneous ignition by self-heating at low ambient temperatures can happen with lithium-ion batteries. This being one of the pinnacles of reactivity of the system. If a system were to be inert, like a piece of wood, self-heating ignition will be very hard, as it is actually. Wood can self-ignite, but it's really hard for wood to self-ignite. And lithium-ion battery is not that difficult for it to ignite at low ambient temperatures. There is a need to have more research that is looking into the module and the pack scales, and that looks into detection and suppression and compartmentation. And that we need closer collaborations between industry and research, in particular between the battery and the fire safety communities. There are two communities that have grown separated, the battery and the fire safety engineering together, which should look for integration and harmonization across sectors. And to emphasize the premise that better understanding of lithium-ion battery fires will enable innovation, better batteries, better solutions, and safer world. this, I finish. I want to thank my collaborators, in particular Francesco, Swansea, Senwen, Xinjiang, Laura, and Greg, and obviously HAZLab, my group, and the electrochemical group at Imperial College, and all my wonderful researchers that work with me, and the sponsors that have believed in our work and has helped us to be where we are. And with this, I finish. Thank you very much.
Hello, welcome back to the Q&A section. Thank you for the professor giving us this delightful sharing. Actually, I want to apologize there for the start of the event. I think there are some technical issues. The sound doesn't really go through with the slide that I'm presenting. So at the moment, I really apologize for these technical issues. But let's welcome Professor Rain to join us in the Q&A section. So please do post your questions to the Q&A box at the moment. So you just post it, then we will just read it out, and then the professor will answer your questions accordingly. Yes. So let's welcome Professor Rain.
Hello.
Hello, good morning, Professor Rain.
Hello, hello, can you hear me?
Yes, good to hear you today.
Excellent.
Yes.
I'm here in London.
Right. Yeah, sorry, let me say, I am Gerald, and then the one next to me is the Hong Kong IE Fire Division Chair Lady, Dr. Fiona Choi.
Hello, Professor Rain, thank you, and nice to learn from you.
Thank you. Thank you for this opportunity to speak to your audience and the invitation to be remotely here today. Thank you.
Right. So we have several questions from the attendance people. The first one they ask is about what sort of detectors is good for, sorry, bear with me for a minute. So yes, what kind of fire detection system is the most appropriate for battery fire? Smoke or heat or any other kind you recommend?
That's a good question. It is indeed a very important question. Very few research papers or industry leaders are able to answer it clearly. What I can say is detecting the smoke, as we typically do with fire, is okay for the detection of a battery fire. But because battery fires are very quick and very violent, detecting the smoke might mean that it's too late to actually act meaningful against a battery fire. That is why, for example, there is a wish to have sensors inside the battery package that are able to indicate that the battery is on its way to failure, kind of like a prognosis and an early warning that something is going on that is wrong with the battery in its electrochemical potential, in the voltage, in the deformation of the battery, in heat development. And this can actually be done with what is called the battery management system, which is a little thinking unit, a smart unit that actually is obtaining basic information from the battery. The battery management system can be used, and there are people who want to use it as a way to foresee that the failure is gonna fail.
Right. Okay, I see. Good. And then we have the next question is about, I think it's regarding the testing that you did or your team did. Is they actually asked what state of charge were your batteries during testing?
Yeah, that's a good question. We use the state of charge that is recommended for storage, which right now, I don't remember. I think it's in the order of 60%, but maybe I'm wrong, and maybe it's 30%. But we use the state of charge that is recommended by manufacturers when the cells are being stored in a warehouse or being transported. It's just before use. I can say that since then, we have actually done additional experiments, actually in USTC in China, in Hefei, one of the biggest fire groups in the world, where we have studied the effect of the state of charge. And we can see how, as the state of charge increases, the self-heating potential greatly increases with the state of charge.
Oh, I see. And there's another question about the testing ability. In one of your slides, you showed that in one of the graphs showed the when X is equal to 1, which is having about 200 battery cells within one box. Why it has a higher critical ambient temperature than the others? Because I think your graph actually have a tick. It's more like a tick to the end.
It is. So the packing ratio equal to 1 is an impossible situation.
Right.
It's a situation where the whole volume of box is battery, and that's impossible because batteries have shapes and they never match perfectly with each other, right? We did this simulation as an exercise of a bounding situation where it will literally be the worst case scenario where the whole box is full. Interesting enough is that the result is that the critical temperature is higher, and that is because the battery itself has a different conductivity than the spacing. So we add it as an ideal bounding case, but it's not possible to attain it.
Right. Okay, I see. So we have another question coming through, and they actually ask is, Professor, in order to prevent battery fires, what is the best operating temperature for the battery? Because you said that sometimes they may ignite in ambient rather than accidental, maybe leak gauge. So what is the best temperature you recommend for battery to operate in?
Operating, that it will be out of my expertise.
Right.
But the literature has been trying to answer that question for a significant amount of time. If the battery is operating, if the battery is being charged and discharged, which is what batteries are meant to do, the temperature of the battery is the result of many different reactions and heat transfer processes. So itself, what you want is you don't want the battery to be too hot because it can actually undergo self-heating, but you don't want it to be too cold or because the battery has the efficiency of the battery is actually significantly affected by its temperature.
Right.
The results that I show, I want to emphasize this, is when the battery is not charging, not discharging, is being stored in open circuits, so it's not operating. And we use this because if we can see self-heating even when it's not operating, it means that when it's operating, everything will be much more reactive. So that the temperatures that we see here, when it's not operated, it's an upper bound. And if it's operating, then all the critical temperatures will decrease tremendously because additional reactions that are exothermic take place when the battery is operating.
Okay, I see. Right, we have another questions come through. Is asking about nowadays for car parks, we have so many EV cars, and for normal building, do you think that the sprinkler system is good enough to control the battery expansion, or because you have mentioned several type of ignite put out the fire, like having a tank just cover the car is the most efficient to flood it out. But do you think sprinkler will be efficient enough?
That's a very, very good question. Obviously, it's in the mind of every single engineer. And the short answer is no. The sprinkler system that has been designed to deal with furniture fires and car fires is not enough to handle a battery, an electric vehicle battery. However, it's better than nothing. It would definitely provide protection. The sprinkler system will definitely provide protection. It will make the fire smaller for some amount of time until the fire brigade arrives. But the sprinkler system has been shown that it's not with water, just simple water, is not able to stop a burning electric vehicle because of the battery. And this is a discussion that we had often with the fire brigades, and the fire brigades are seriously concerned about how to handle electric vehicle fires because they know that the battery could be burning for days.
Right.
And so, and it's not a matter of removing the oxygen. It's not a matter of covering it. It's a matter that what is the concept of strain energy is a concept that has appeared because of electric vehicle fires. Stranded energy means there is energy in the battery and there is no way to get it out. And if we don't get it out, it will come out as a fire. And that's what the fire brigades, it started in the Netherlands, but actually even I think Tesla recommends this. They recommend to immerse the whole vehicle or at least the package, if it can be extracted, into a tank of water with salt. And that, which is it's a brutal way of suppressing the fire, is a fail-safe, a way that we will convince that it will really stop the fire.
Right. Okay. Probably you answered another question as well, because one of the audience asked, what kind of suppression system is suitable for battery fire? So probably is to immerse the whole battery into some water and cool it down and make it.
For example, it's a good question. For example, there are not many studies in the literature. I've been doing fire science as fire engineering for the last 20 years. So I know the type of knowledge and depth that we need from serious fire hazard. There is very little knowledge on how to deal with battery fires and the suppression. But for example, there is breakthroughs by the insurance company FN Global, which are very concerned about fires in storage facilities. And they have proven that they can develop methods of suppression based on water that can alleviate or mitigate the loss of a fire in a storage facility. But it's not it doesn't operate the same way as the traditional sprinkler. And actually there is ongoing research if there is a need to replace the liquid, the fluid that is actually used in the sprinkler, and to study how to direct the jet of water into in the site of a fire, etc. So ongoing work, a lot of work being done as we speak, because the question that has been asked is the question that many people is asking.
Right. Okay, I see. So another question come through is related to this it seems that the battery fire can be considered as electrical fires. For example, for the vehicle fire, battery fire, is it not prefer to use water-based suppression system because it is more electricity-based?
Yeah, good point. There is a little bit of research that has been looking into different liquids, different fluids, and even different gases. Precisely because knowing that water is conductive and maybe it's not what you need for a battery. But I can tell you so far it's not been found. The situation has got the industry unprepared to deal with fire phenomena that is so complex, and it has been, to tell you the truth, battery fires have been happening for the last 20 years. But the industry, the lithium-ion battery industry, manufacturers or users, have not been interested in looking into this for a really long time. Now they are. Now, I would say over the last 3 years, they have shown an open and honest worry about this. But there is a lot. What I mean is that the need to have these answers requires time to do the studies, and the answers will not come in a rush just because there is a need for the question.
Right. Okay, I see. So we have another question. Is larger battery like car battery or bus battery is more hazardous than the small battery like cell phones, or they are equally dangerous?
No, obviously, as in fire engineering, the larger the battery, the more the energy is inside. So the more violent and the more powerful would be the resulting fire. And it can escalate quite quickly. Interesting enough is that it could be that the smaller batteries, when they have a defect or when they have been designed not properly, they might be more prone to ignition than the larger ones. It could be. So then we could be in a situation where the smaller batteries ignite more often, but they don't lead to massive fires, whereas the largest batteries don't ignite as often, but lead to catastrophic fires.
Right. Okay. And we have another question is there any common material for housing the lithium battery in fire safety purpose?
Sorry, can you repeat the question?
Is there any common material for housing the lithium ion in fire safety purpose?
There is no agreement in the literature. What people are trying to do is they're trying to find tough containers. They first went to steel. They actually went to a steel box. Boeing did this. I don't know if you remember that in 2013, when the Boeing Dreamliner started to fly around. Within 2 weeks, there were like 7 battery fires. And the answer for Boeing was to encase the batteries in metal boxes. tough metal boxes. They call it sealed containers. That is a compartmentation protection layer. It means that if the battery fails, at least it would not endanger the aircraft. Interesting enough is that by putting these tough containers that are sealed, they are removing the ability of the battery to dissipate heat. They're actually stopping cooling. So actually, they might be controlling the damage if a battery fails, but they might be promoting the failure of the battery by not allowing the battery to cool down.
To cool down, right? Okay, I see. So nowadays, the lithium-ion battery is one of the most common battery now in use, but it seems that the fire hazard is quite high. Is there any potential product that can be used to replace lithium battery ion? Maybe I heard that like hydrogen battery is coming up in this couple of years. Will it have less hazardous than the lithium ion?
Maybe it's a good question. I don't really know. I know that the industry, the battery industry, is always coming up with new chemistries. And they always aim to have higher energy density. This is really what makes the product successful. And only afterwards, and after many years, they start to also see if their chemistry is more or less flammable, or it actually promotes or not self-heating. So it always, safety, as it happens very often in fire engineering, unfortunately comes afterwards, having a product already been launched. About the hydrogen cell and the fuel cells, the hydrogen is also a flammable material, which has quite energetic. So fuel cells are not exempt. They do from flammability issues, but so far they don't seem to be so unique as the lithium-ion battery. The hydrogen safety is much similar to the safety of gasoline and diesel cars and methane. Right. Okay, I see. So we have most of the question answered. Is there any question? Please do post to the Q&A box so that we can share your concern with Professor. It is quite delightful that we have people that have so experience in sharing with us. So, Fiona, do you have any question to ask?
Yes, I have a question for Professor Wayne. It's very knowledgeable to know that you explained the behavior of the lithium-ion battery. Say, we understand that under the ambient temperature, it will self-ignite, and then to stage 2, stage 3, it will have a runaway. It's very special behavior. And when correlated to real life, what we think about is that, say, for example, this will happen in our cell phone, and the cell phone during the storage, and then also when disposal, it will be sit together for certain size and capacity. And that is one case. And another case, probably not the cell phone or the battery used for the car, and it is during the storage. I just think any research or literature had consider or will study the arrangement for storage, the environment, say the quantity to limit it, not to put together or any separation or ventilations. Is it, how would these subjects in the research awareness? And again.
Thank you. I'm very happy for that question. Thank you very much, Samantha. Actually, I'm happy to say that one of my PhD students at Imperial College, he is a Chinese national, is Sen Wen Hu. His PhD thesis, which is finishing in 1 year, is precisely to answer your question about is developing an understanding of self-heating during storage, and what he's using immediately is to develop solutions, storage solutions of how to store these batteries such that they don't promote self-heating. And the work of Zhengwen is actually supported by Xuanze He, which is another PhD student of mine from a national from China, who is also experimentally doing this work, and you already saw some of his work. So if you wait 1 year, Samantha, Swansea and Senwen will give you the answer, hopefully.
Oh, that would be great. Thank you.
Thank you. So is there any more questions from the audience? Please do feel free to text it into the Q&A boxes. So probably I think we have one more question coming through. Is what is your opinion on suitability of aircraft fire suspension system for battery fires, and any chance you think they are needed?
What is this? What is the name of the system again?
Is actually, what is your opinion of a suitability of aircraft fire suspension system for battery fires?
Aircraft suppression system. That's quite interesting. I've actually been asked to provide opinion on this. And my understanding is that they currently don't have one, right? Or well, it could be for cargo airplanes. Okay, so the research unfortunately is very thin, and we don't really know what's the way forward. But everybody should be encouraged to look into this, because if we know how to extinguish battery fires and how to detect them, immediately airplanes and transport systems and houses and warehouses can actually have this technology. So my view on this is that unfortunately we need more feedback from industry and more efforts from science to see the way forward.
Right. Okay, I see. So we have one more question on for some fire code in some countries has started to require separate fire compartments for car charging stations. Just hearing that the sprinkler may not be the most efficient to suppress, is this the only practical solution available now?
Well, so it's a good question. That's why we emphasize these 4 layers. I mean, in reality, there are 6 layers, and all layers of protection need to be in place with different depths, so to speak. It is not acceptable in current situations to use just one layer. It's not enough to say, well, I have a sprinkler. That's not enough. Everybody has to work on the prevention to make sure that the battery doesn't self-ignite or thermal runaway. It is important that we have detection. It is important that we have suppression and that we have compartmentation. And when people are going to be around the system, as it happens in airplanes or in buses or in cars, there is an additional layer which is very important, which is evacuation. If we detect the fire, the first thing that we actually need to do with that signal of detection is to order an evacuation of people nearby. I mean, if you're an airplane and you're flying, the first thing that you need to do when you have a detection is to land the airplane and people evacuate. So the evacuation layer is also a very important protection layer. So the answer to that question is we could do many things, but the best thing is to explore all the possible layers, not just rely on one single one.
Right. Okay, I see. So we don't have more questions to come through. So so probably I will have it to be an end. But before that, I would like to hand over to Dr. Fiona Choi to say a few words to thank you, Dr. Rain and all the other people as well.
Oh, thank you, Gerald. On behalf of 5 divisions of Hong Kong Institutions of Engineers, I would like to first thank you, Professor Rain, to give us this very fruitful and valuable research knowledge sharing. And in fact, it can be held without geographical limitations. And I know that Professor Rain prepared this till yesterday night and to give us this very good findings and sharings. And this event is also very meaningful to our divisions. And actually, our division will arrange overseas visits yearly But in last year and the year before, it cannot be held because we all need to maintain social distancing. However, this does not limit us to continuous learning from not only locally but also overseas. And we are pleased to have our organizing chairman Gerald to make this sharings without the geographical boundary. And in fact, this only can happen with the close coordination and collaborations with the Australian counterparts, the HKIE of Australian chapter, plus the Society of Fire Safety in New South Wales. And of course, the audience and speaker from London. So it's a very unlimited geographical boundary. And also we are pleased to share the latest research findings, and very glad to hear the ongoing research by Professor Ring's research students that we are also interested, and we hope that in the future we can help similar or to have the continuous linkage and sharing. We are very pleased, and thank you, Professor Ring, and also thank you, Gerald, to make this sharing happen.
Right.
And I'll hand over the time to Gerald.
Okay, thank you, Fiona. Definitely, I think, as I said, I apologize for the start of the event. There are some technical issue that the sound doesn't go through. So I definitely want to take this opportunity to thank you, Ms. Angeline Mayon from the Australian chapter Hong Kong IE, and also Edward Ong, who actually introduced me to Professor Ring to make this event happen. And he is in this event. He definitely showed me that he will join this event and make sure he will say hello to you. So thank you for everyone joining us for this event. So we may make it as a close for the event. Then the CPD search, we will send it back to you shortly. So remember to have your name and your registered Hong Kong IE numbers to fill in at the Q&A boxes. Then we will send the CPD back to people later. Thank you very much for everyone.
And have a good night.
Have a good night. Okay.
Thank you.